So section 9.4, transition diagrams and matrices. A transition matrix is a square matrix that shows a change from one state to another state, where the change follows the same set of rules each time. So let's look at this particular example, which involves some shopping centres. So this left-hand side here is a transition diagram. You'll notice that we have 2 points which represent the two shopping centres, shopping centre E and shopping centre H. We have lines moving away from those points, and there are percentages on those lines. So from shopping centre H, we have an arrow or a line moving out with an arrow going this way back into H, and that shows that 90% of the customers that were shopping at shopping centre H in 1 week will remain to shop the next week. It also shows that 10% of those customers that were shopping in a particular week will move across to shopping centre E the next week. And if we take the perspective of shopping centre E, this shows that 75% of shoppers who shop at shopping centre E in a particular week will continue to shop there the next week, and 25% will move across to shopping centre H. So this is a transition diagram. You'll notice that all of the lines moving away from a point need to add up to 100. And we can also show this same information in a transition matrix. So remember we said it was a square matrix. We've got two different states there. So we've got E and H, and so it's a 2 by 2 matrix. The transition matrix is usually denoted as a capital T. And you can see that we've represented this information in this particular matrix. So if the best way of looking at it is from the top here, it's always from and to. So from this week to next week. And if we look at shopping centre E, this 0.75 represents that 75% of customers in a particular week will continue to remain customers at shopping centre E. And therefore 25% will move across to shopping centre H. So these add up to 1. And then with the H, we can see that 90% of the H customers will continue to shop at shopping centre H the next week, and 10% will move across to shopping centre E. So the columns add up to 1 to represent that 100%, and you've got from E to E and H to H there. So the main points here, transition diagrams show transitions using percentages, so we've already spoken about that. In a transition diagram, all the arrow percentages from a single point add up to 100. Transition matrices give the percentage from the transition diagram as decimals, so you can see the 75% is 0.75, and each value in the transition matrix needs to be a value between 0 and 1, and the columns add up to 1 exactly, and that will always be the case. All right, so in this example we have a transition diagram, and we've got 3 points A, B and C. And we're looking at the movement from point to point. So as an example, from point A, we can see that 65% maintain to be at A in the next transition, 5% move across to C, and an unknown X percentage move across to B. Now remember that all of the arrows moving away from point A need to add up to 100%. So we've got X plus 65 plus 5 equals 100. So that must mean that X is 30%. So this unknown amount that moves across to B is 30%. From B, we've got 45% who remain at B. We've got 35% who will move to A, and an unknown Y percent that will move across to C. So again, all of those percentages need to add up to 100. So Y is equal to 20%. Finally, for C, we've got 40% that will move across to A. We've got an unknown Z percent that will remain at C. And we've got 50% that will move across to B. We add all those percentages together, and the only thing that's unknown is Z, and so Z is 10%. So there's our Z. We now want to represent that as a transition matrix. So we've got from and to. So if we put our different points in, A, B, C, and then maintain that same order, A, B, C, This leading diagonal will represent the percentage that will stay at that same point. So 65% will remain at A from state to state, 45% will remain at B, and 10% will remain at C. So that's that leading diagonal. Remembering that everything needs to add up to 100% or 1. So if we take the point of A, then we've got going from A to B. So from A to B was that unknown X, which we've already solved as being 30%. So we put in 0.3. We've also got from A to C, and that is 5%. So we put in 0.05 because that's what 5% is equal to as a decimal. And we work our way through the matrix. Remember, it's always from and to. So from C to A, so from C going to A, we've got 40%, so that's 0.4. From C to B, so from C to B is 50%, therefore 0.5. And from C back to C is that unknown Z, which we solved as being 10%, so therefore 0.1. Okay, so this time it's a little bit reversed in that we've been given a transition matrix. We're going from A, B, C, that's the current state, to the next state, so from and to. And again, A, B, C, same order. Remembering that all of the columns need to add up to 1. And obviously there's some unknowns here. So we've got an unknown X, and obviously X needs to be equal to 0.4 so that this column adds up to 1. An unknown Y, and that needs to be equal to 0.3 so that this column adds up to 1. And an unknown Z, and given that these are both zeros, Z itself needs to be 1 so that it adds up to 1. And we need to show this as a transition diagram. So here I've got all the crucial bits of information. Let's go back a little bit. So if we take the perspective of just drawing your dots for a starter, so dot A, dot B, dot C, and then show the loops. So the loops, remember, show that what percentage maintain that same position. So 20% go from A back to A, that's there. 0.1, 10% will go from B back to B. So along here needs to be that 10%. Oh, sorry, and I've gone this way with the arrow, 10%. And Z is equal to 1, so 100% of those who are at C will remain at C. And then just work your way through. So obviously from C, there's no arrow that connects back to A, so we don't even need to show that. And C going to B, there's no percentage that leaves C that goes to B, so we don't need to show that either. And that's basically it. So here we've got example 2. And basically it's all about this transition diagram. We're looking at birds, and they nest in location A, B, and C in this particular year, and then move across to locations A, B, and C the following year. Now originally there are 400 birds in location A, 660 in location B, and 210 in location C. And you can see as they move across from location to location from one year to the next is given. So as an example, this 0.4 represents that 40% of the birds in a particular year will go and nest in location A again the next year. First question, how many birds nesting in location B, so this is from B, would be nesting in location C the next year? So we're going from B to C. So you can see here we've got this 0.25. So in other words, 25% of the population of B will transition across to nest in C the next year. So from B to C is 0.25, so 25% of the population that are in B. So there's 660 birds at the beginning in B, so we want to work out what 25% of 660 is. So it's just 0.25 times 660 gives us 165 birds. Similar kind of question. We need to work out how many birds nesting in C this year would be nesting in C the next year. So we're going from C to C. So you can see here that 70% of the birds who nest at location C in a particular year will continue to nest there the next year. So from C to C is 0.7. So we want to work out 70% of the 210 birds who are nesting at C. So it's just 0.7 times 210 gives us 147 birds. And C will be, how many birds will be in location A next year? So they are actually in A. So 40% of the A population will go to A, 20% of the B population will go to A, and 30% of the C population will go to A. So this is going from these various locations to A. So 40% from A to A, 20% of B go to A, and 30% of C go to A. Now we know that there are 400 birds in A, 660 initially in B, and 210 in C. So we just have to work out those various percentages, and you can see we get this number of birds. So 160 birds go from A to A, 132 birds go from B to A, and 63 birds go from C to A. So in total, there will be 355 birds that will be in location A next year. D is asking us how many birds will be in the same location the next year. So we're looking at this leading diagonal across, so from A to A, from B to B, and C to C. So 40%, 55%, and 70%, that's just coming through here. So we want to get 40% of 400, we want to get 55% of 660, and we want to get 70% of 210. And you can see it comes up with these figures here. In total, there's 670 birds that will continue the nest in the same location they did the previous year. Alright, so example 3. Find the transition matrix T for each of the following situations. So the first one here that we're looking at is a train arriving. So in your notes, you don't have all of the question. You've only got the first little paragraph here. So if a train arrives at a certain station on time, the next train has an 85% chance of being on time. The second part, which wasn't given to you, if a train arrives at a certain station late, the next train has a 30% chance of being late. So we've got two states here that we're concerned about, being on time and late. So we're going to set ourselves up with a 2x2 matrix. So we've got this train and the next train, from and to. So an 85% chance if we're on time for this train, the next train is 85% likely to be on time also. So with the O to O, on time, we put in 0.85. From this little paragraph, if a train is late, then there's a 30% chance the next train will be late also. So going from late to late is 0.3. So we put those two in. Now remembering that the columns need to add up to 1. So I need to put something in here where my dot is, and obviously that needs to be 0.15 so that those two add together to get myself 1. So that's where we get the 0.15, and I need to put in 0.7 here so that this column adds up to 1. So the 0.7 means that if a train is late, there is a 70% chance that the next train will be on time. So in this second example of a transition matrix, we've got this student, Laszlo, who follows a system of answering multi-choice questions in an exam or a test. So he has 5 options, A, B, C, D, and E. And these dot points show how he makes the next selection. So he will basically work through these dot points to create this transition matrix below. But given that we've got 5 different locations or states there that we can consider, and every transition matrix needs to be a square matrix, we're obviously going to have ourselves a 5x5 matrix. So that's shown here. So we've got from this question to the next question going down. Let's work our way through. He never picks the same option twice in a row. So if we chose A, there's a 0% chance it would choose A again. If we chose B, there's a 0% chance it would choose B again, and so on. So across this leading diagonal, we have zeros, and that's from the first dot point. If he has picked D, he will always choose C next. All right, so here we're going from D to the next question, and we are told that if he has chosen D, the very next question he will always choose C. So from D to C needs to put in a 1, and then everywhere else we can put in zeros from D to D. If he has picked E, he always chooses A next. So if we've chosen question E, then it's 100% likely that he will choose A next. So we put in a 1 there, and everywhere else we can put in zeros. And if he has picked A, B, or C, he tosses a coin to decide which of the next two alphabetical order he will choose next. Alright, so what that means is that if we've chosen A, he will either choose B or C because they are the next two in alphabetical order, and it's a 50-50 chance because he's just going to toss a coin to decide. So it's 0.5 of a chance that he'll choose B and 0.5 of a chance he'll choose C. Everything else below needs to be zeros because he wouldn't consider doing that. Now B has the same rule. So if we choose B, he will either move across to C or D. And again, to decide, he will toss a coin. And then the same thing for C. So if he's chosen C, he'll either go to D or E because they are the next two options in alphabetical order after C. And it's a 50-50 chance again, so he'll toss a coin to decide on that. So we've got everything there, and you'll notice that all of these columns now add up to 1. So each column adds up to 1, so we've got everything that we need, and everywhere else there should be zeros. So finally, that shows us this matrix here, which is the final answer. That's how we created it. Obviously, I don't recommend that you go with that kind of strategy for your end of year exam.